Hi, in this video I'm going to give you a proof of the famous Chinese remainder theorem from number theory. Yeah, so this is the statement of the Chinese remainder theorem. Let n1, n2, etc. nr be positive integers such that ni and nj are relatively prime. That means ni and nj are pairwise relatively prime. That means say that GCD of ni and nj is 1 for I not equal to j. Then the system of linear congruences x congruent to a1 mod n1, x congruent to a2 mod n2, etc. x congruent to ar mod nr has a simultaneous solution which is going to be unique modulo n1 into etc. nr. So as you can see from the statement of the theorem, this theorem is applicable to very much useful to solve a system of linear congruences x congruent to a1 mod n1, x congruent to a2 mod n2, etc. x congruent to ar mod nr. So if such is a system of linear congruences and we are supposed to find a simultaneous solution, then the theorem says that as long as these ni's are pairwise relatively prime, then this system will always have a unique solution which is going to be unique modulo n1 into etc. nr. The proof for this goes as follows. To begin with, we'll take n to be equal to the product of all ni's n1 into etc. nr, and we'll also take capital Ni equal to n divided by ni for each I equal to 1, 2, 3 etc. r. Here this means that capital N1 is basically n divided by n1, which is the product n1 into etc. nr except n1. So capital N1 will be equal to n2, n3 etc. into nr. The same way capital N2 is going to be equal to n1, n3, n4 etc. nr and so on. So each capital Ni will be the product of all ni's except the corresponding small ni. Okay. Now since ni's are pairwise relatively prime, GCD of capital Ni comma small ni is going to be 1. This is because capital Ni is a product of all ni's except this ni. So accordingly, there is no common divisor between these two except 1, which is positive. So accordingly, the GCD is going to be 1. Now, because the GCD of capital Ni comma small ni is going to be 1, we see that the linear congruence capital Ni x congruent to 1 mod ni will have a unique solution. This follows from the fact that Ax congruent to b mod n is going to have a unique solution as long as a and n are relatively prime, right? So accordingly, capital Nix is congruent to 1 mod ni is always going to have a unique solution for each I varying from 1 to r. That means to say that capital N1 x is congruent to 1 mod n1, capital N2 x congruent to 1 mod n2 and so on, capital Nr x congruent to 1 mod nr. Fine. Now if we assume that each of these linear congruences will have a solution, say xi, that means to say that x1 is going to be a solution of the unique solution of n1 x congruent to 1 mod n1, x2 is the solution of n2 x congruent to 1 mod n2 and so on. We see that n1 x1 is congruent to 1 mod n1, n2 x2 is congruent to 1 mod n2 etc. nr xr is congruent to 1 mod nr. Okay. Now if these xi's are the solutions of the corresponding linear congruences, now we are going to show that x bar, which is basically the sum of this product ai, ni, xi, I varying from 1 to r, is going to be a simultaneous solution of the given system. Now what do you mean by this expression? This is going to be a1 n1 x1 plus a2 n2 x2 plus a3 n3 x3 and so on ar nr xr. So this sum, if we denote it by x bar, now we are going to show that this is going to be a simultaneous solution of the given system. Now to prove this, to understand this part of the proof, I'm going to give you a short illustration. Now n1 divides n2, n1 divides n3 etc. n1 divides nr. As we know, capital N2 is basically small n1 into small n3 etc. small nr. So this will have everything except n2. So n1 automatically divides n2. The same way n1 also divides n3 because n3 will have n1 as a part of it. The same way n1 is a part of every capital Ni except capital N1. So it divides each of these Ni's from N2 to NR, right? Accordingly, N1 divides a combination of these. I will choose a combination to be A2 N2 X2 plus A3 N3 X3 plus A4 N4 X4 and so on plus AR NR XR. Okay. Now, accordingly, we know that, coming back to the original slide here, we know that capital Ni Xi is congruent to 1 mod Ni, right? Accordingly, capital Ni Xi is congruent to 1 mod Ni for each I implies capital N1 X1 is congruent to 1 mod N1, which means to say that N1 divides capital N1 X1 minus 1, right? Now, if N1 divides capital N1 X1 minus 1, then N1 also divides A1 into this expression, which is going to give you A1 N1 X1 minus A1. Now, in terms of writing this expression and this expression combined together, we are going to see that N1 divides this expression and N1 divides this expression implies N1 divides this plus this, which is basically A1 N1 X1. This minus A1, I am going to write it at the end, and I am going to write the rest of the expression here as such here. Now, what is the advantage of having it this way? Now, if you observe this, this is N1 divides A1 N1 X1 plus A2 N2 X2 plus A3 N3 X3 and so on plus AR NR XR minus A1. Here, this expression A1 N1 X1 plus A2 N2 X2 plus etc. plus AR NR XR is basically what is X bar. So, N1 divides X bar minus A1. And in terms of congruences, this can be understood as X bar congruent to A1 mod N1. Right? Now, this shows that X bar is congruent to A1 mod N1, which means to say that X bar is a solution of X congruent to A1 mod N1. Likewise, instead of taking N1 here, if we choose N2, then we can see that N2 divides capital N1, N2 divides capital N3, etc. N2 divides capital NR, and that ultimately gives us, following the same pattern, it gives us N2 divides X bar minus A2, which means that X bar is going to be congruent to A2 mod N2. Likewise, going this way, we see that X bar is congruent to every AI mod Ni. Now, this is given generally here in the following steps. So, first of all, as we saw here, N1 divides each of the capital Ni's except N1, right? Capital N1. Accordingly, Ni divides every capital Nj except j equal to I. Correct? So, small ni divides capital Nj, which means that small ni divides Aj capital Nj xj. And that implies that, again, here capital Ni xi is congruent to 1 mod Ni, implies that Ni, small ni divides capital Ni xi minus 1, so that Ni also divides Ai into capital Ni xi minus 1, which is Ai Ni xi minus Ai. Now, Ni divides Aj Nj xj for all j from 1 to r, and Ni divides this expression, combining which is going to give us Ni dividing A1 N1 X1 plus A2 N2 X2 plus etc. plus AR NR XR minus AI. And as we saw earlier, this expression is nothing but, see, A1 N1 X1 plus A2 N2 X2 plus etc. plus AR NR XR is nothing but X bar. So this is going to give us Ni dividing X bar minus AI. And Ni divides X bar minus AI means that X bar is congruent to AI mod Ni for each I equal to 1, 2, 3, etc. R. Now, what does that mean? It means that X bar is a solution of A1 mod N, X bar is a solution of X congruent to A1 mod N1, X bar is a solution of X congruent to A2 mod N2, etc. X bar is a solution of X congruent to AR mod NR. So that means that X bar is a simultaneous solution of the given system of linear congruences. Right? So this means that there is a simultaneous solution for the given system of linear congruences as long as these small ni's are relatively prime, pairwise. Right? Now, that's not the end of the proof, because if you go back to the statement, the statement says that this has a simultaneous solution, which is what we have proved just now, but we are also supposed to show that this solution is unique modulo n1 n2 etc. nr. Right? Now we are going to prove that part of the theorem now. So to prove that x bar is a unique solution, to show that the solution is unique modulo n1 into etc. nr, which is n, we will choose x dash to be another solution of the given system. So x bar is one solution and x dash is also another solution of the given system. So that means to say that x bar is congruent to ai mod ni and x dash is congruent to ai mod ni for each I from 1 to r. Now x bar congruent to ai mod ni and x dash congruent to ai mod ni implies that x bar is congruent to x dash mod ni. This is basically following one of the fundamental properties of congruences. So x bar congruent to x dash mod ni for each I. That means that ni divides x bar minus x dash for each I. And ni divides x bar minus x dash for each I implies that n1 divides x bar minus x dash, n2 divides x bar minus x dash, n3 divides x bar minus x dash, and so on. nr divides x bar minus x dash, and that means that n1 into n2 into n3 etc. into nr divides x bar minus x naught. This is because each of these ni's is going to be relatively prime with all the other ni's, right? So the product also divides x bar minus x dash. And what is this product basically? This product is what we have chosen as n. So this means that n itself divides x bar minus x dash. And what does this mean in terms of congruences? N divides x bar minus x dash implies that x bar is congruent to x dash mod n. And what does this mean? This means that x bar and x dash are the same under modulo n, which means that x bar is unique modulo n, which is n1 into etc. nr. So this proves that the solution x bar that we have achieved, which is given by, what is x bar given by? X bar is basically the expression a1 n1 x1 plus a2 n2 x2 and so on plus ar and xr is going to be a simultaneous solution, and it is going to be unique modulo n1 into etc. nr. So this completes a proof of this theorem. Now this proof itself is what is being used to solve problems also. So if you remember the previous presentation that I have given on Chinese remainder theorem, where I have illustrated some problems which are solved using Chinese remainder theorem, this expression for x bar itself is being used there. So there we are going to construct each of these systems capital Ni x congruent to 1 mod Ni. We are going to solve them and find out each xi's, and once we have got each xi's, x bar is going to be given by a1 n1 x1 plus a2 into x2 etc. plus ar and xr. This is how we are going to use this particular theorem to solve a system of linear congruences. Mind you, this is applicable only when each of these small ni's are relatively prime. So this part is going to be very important. Each ni and nj, each pair ni and nj is going to be relatively prime for I not equal to j. Only if this happens, we are going to solve this using Chinese remainder theorem. Fine. So this is the proof of Chinese remainder theorem. So thank you for the patient listening. Go through the proof once again and get back to me if you are not able to follow any part of the proof. With this, I'm going to conclude this presentation. So thank you once again. Work hard, work smart, and prepare well. Have a good day. See you.